Good morning. My name is Cody Knowles. We're Team 7, and our facilitator is Dr. Ayers, who's right there. And we're being sponsored by the Department of Pharmacology and Toxicology to produce a small animal Barostat instrument for research purposes. So we have the privilege this semester of working with Dr. James Galligan. He's the Associate Director of Neurosciences in the Department of Pharmacology and Toxicology. And he's studying IBS, or irritable bowel syndrome. This is a really common disease in America, more than other countries for some reason, with symptoms such as nausea, diarrhea, abdominal bloating, and pain. Pain being the most important of those. The reason that this study is being looked into is because this abdominal bloating and pain causes such severe discomfort in most patients of IBS that they find it hard to function, and it's a horrible, horrible thing. The exact cause of IBS is yet unknown, hence the research, but some theories think that there could be a direct link between the existence of irritable bowel syndrome and the body's inability to produce serotonin. For this reason, Dr. Galligan is using biologically altered rats in his research. Now, these rats are biologically altered to be without a serotonin delivery system. And the test is run as follows. It involves taking a pressurized balloon and putting it inside the rectum of the test subject, inflating that to a desired pressure, and then observing the muscular response of the test subject. The problem with this, however, is that the balloon is being inflated currently by a lab assistant operating a syringe. So simply, pushing that in there and inflating it. And as you can imagine, this introduces a lot of error. So this is what we're talking about. Ideally, we would like the pressure curve to look like this. Now this is a graph of the pressure inside the balloon during one 30-second long test. Ideally, we would like 10 seconds of uninflated balloons, 10 seconds at our desired pressure, and 10 seconds off to let the gastrointestinal tract, or GI tract, of the animal get back down and settle to rest. Currently, though, this is what we're looking at. As you can see, we have 3 points of concern that we hope our design will address. Firstly is this little bump right here. Now, this bump is actually a direct remnant of the lab assistant's thumb tensing up as he's about to push in the syringe. And so you get a little bit of human error right here. Secondly, and probably most importantly, is this. You can see this rises instantaneously. Now, this has a slow rise time to it of the order of 3 to 4 seconds. And this is because the lab assistant has to really concentrate not to overinflate the balloon and hurt the animal. So it has to be really, really slow. So we hope to correct that. Another thing is, in addition to these little bumps, which are natural, you see we have these large peaks and valleys here. This is actually due to the gastrointestinal tract of the animal constricting and relaxing and creating pressure changes in the balloon. And we hope to get rid of those with our design as well. So the device in question that can accomplish all this is called a Barostat. As the name implies, it is simply a device that can output a desired pressure level, maintain that pressure level, and measure it and show you what pressure is currently at. And currently on the market, this is available. It's called a Distender IAR. It's designed specifically for rats, has all the necessary features, and is designed to operate in the correct pressure range that we want. The problem with this, though, however, is we did our research and we found that this device was designed and created by a single guy in Canada, and they're made out of his basement. Now, these are the only device of this kind on the market that are commercially available, and because of this mini monopoly that he has, he's had no incentive to redesign it or offer any sort of competitive pricing. For this reason, we're working with very old technology, 1992, and he's asking almost $26,000 for it. So one of our design objectives is to create a similar device that can do all the same things, but for a much more cost-effective price. This is our FAST diagram, just outlining the things that we hope to accomplish with our device. Essentially, we would like a device that can receive an input pressure, desired pressure value, and hold the pressurized balloon at that pressure using a feedback sensor. Now, This, the microcontroller in our device would directly operate with a stepper motor, which will simply push in or pull out the syringe, effectively increasing or decreasing the pressure of the test. Again, we'd like to automate this test and get rid of all human error as much as possible.
Hi, I'm Jacob Scott. I'm going to talk to you about our design process and the designs we kind of went through here. Our initial design idea was actually to use an air pump to drive or to pressurize the system. Basically, this used a commercially available medical air pump, low pressure pump, to pressurize the system, and then it used a sequence of actually air solenoids used to either vent air from the balloon, fill air, send air to the balloon, and also to control the flow from the pump to prevent air from leaking back through the pump when it was off. This system used 2 air pressure sensors, low pressure sensors, high precision, to actually provide feedback to the control system. And we actually ended up with this design coming up with the idea for a pressure reservoir to just compensate for different issues you might have with the pump, like when the pump would first turn on, there's a little lag time before you get air pressure, and ideally, as Cody talked about, we would like the system to fill almost instantaneously. This system was driven by a user interface that consisted of a keypad and a LCD screen and controlled by a thick microcontroller. The advantages of the system is they're really low maintenance. These air pumps are used in quite a few medical devices out there, like blood pressure cuffs, and they're meant to be used for a long period of time with no service. But the disadvantage to the system was that we were unable to actually measure the amount of volume of air going to the balloon, because we just basically had solenoids opening and closing, and to actually come up with a system to measure the small amounts of air going both directions in and out of the balloon was a big design challenge, and turned out to be something that was possible but not very cost effective. Another disadvantage of this design was that it was very complex. I mean, we had all these solenoids, we had had the pump and the reservoir, and ultimately all this led to the fact that it was a very high cost design. And of course the desire here was to reduce the cost. So our final design solution is actually a syringe-driven system, basically using a disposable syringe, much like what they're using for the test in lab right now. This syringe is coupled with a stepper motor. For those of you who don't know what a stepper motor is, basically it's just a DC motor that can be moved in very discrete steps, so we can control its exact position. This system only used a single air solenoid just for venting the air at the end of the test. The desire is for the test, when it ends, to be immediately, ended, and that enabled us to do that. And this also used 2 precision pressure transducers. The system and user interface were actually about the same between the 2 designs, basically used the same control system, but overall it was quite different with the motor and syringe. The advantage of this system, because we were using a stepper motor, and we know the diameter of the syringe, is just a small amount of math to actually calculate per step of the motor how much air is being put into the balloon. And this is desirable because some of the tests they're doing in the lab actually require them to put specific amounts of air into the balloon over time. This design was much simpler than the initial design, fewer parts, easier to assemble, and ultimately that made it a lower cost. The disadvantages are that the syringe has to be periodically replaced because, the term disposable, it is a disposable syringe. It has a limited lifetime, and eventually the rubber plunger in the syringe will begin to stick, and it's going to cause leaks or other problems with the test. The other disadvantage is that the pressurization of the system, because we have to start turning the motor and actually push the syringe in to increase the air initially, there could be a little lag there, which we hope to compensate for by using a larger diameter syringe so that we actually get more air per step. This is a block diagram of our final design. We have our user interface interfacing directly to our control board. The pressure sensor provides constant feedback from the stepper motor, which is controlled directly by the control unit. We have a pressure limit reached condition, which may be because we're in the middle of a test, we've reached the target pressure, in which case we stop the motor and stop filling it. Or it may be at the end of the test where we'll actually use a solenoid to release the pressure immediately. And then this system is also affected by the timer because like Cody said, we have a 10-second duration for the actual pressure test. And then the system actually gives an output to the user so they can actually incorporate into their existing system where they actually put the pressure into a computer and they're able to display the pressure versus time.
My name is Casey Davidson, and I'm going to be discussing with you the part selection as well as the budget for our design. The two primary components of our design is our development board and our pressure sensor. The development board we chose is an ET PIC stamp module. We chose it due to its low cost as well as its versatility. It comes pre-equipped with a PIC processor, which we are very familiar with, allowing us to operate much more easily while doing our tests. It has 65 I/O pins as well as 16 10-bit A-to-D converters and 5 onboard timers, which are capable of doing the high-speed measurements required for the lab testing to try and achieve that instantaneous curve. And finally, it also operates at 5 volts, and this is actually roughly close, very similar to the operating voltage of the stepper motor used in the design, and this allows us to streamline our design by only having to use a single power supply. The pressure sensor we chose is an onboard pressure and force sensor, which is made by Measurement Specialty Sensor. We chose it because it's operational at very low pressures between 0 and 2 psi. This is ideal because our maximum allowed pressure in testing is 80 millimeters of mercury, and this is roughly 1.55 psi. This means that we'll be operating at nearly the entire range of the pressure sensor, which will ultimately increase our resolution. Additionally, it has an onboard amplifier, which eliminates the need for us to include any additional external hardware necessary for amplifying such small signals used in testing. And it is accurate to roughly plus or minus 0.05% and allows the user to actually set a reference pressure along with the input pressure to allow the user to take a pressure differential with a variety of pressure differentials, therefore increasing the versatility of our design. Some of the additional components previously mentioned also are our stepper motor with lead screw attached to the syringe, which will again increase and decrease the pressure inside the balloon. This will be accompanied with an LCD screen and a numeric keypad, which is for the ease of operation of the user. Additionally, will allow the user to implement a variety of inputs as they choose to do so. We will be using a switching power supply due to its small size and low weight, making our design that much more optimal so that we don't have a really big, huge device that we have to lug around and use for testing. And finally, we will include an enclosure to help protect the hardware within the device as well as make it more eye appealing. And then this is a cost matrix representing the total cost of our design currently. And since we're building this design from scratch, so we had to be very cautious about what components we would include as well as the cost of all of those individual components. As it stands, we are under budget. We're going to be looking at about $300 of our allowed $500 budget. And this is good because it gives us the flexibility of changing components if they end up not meeting the specifications required, as well as building the housing within the enclosure to hold our hardware in place, protecting it. And the nice thing about this as well is it gives us the opportunity to meet our goal of replicating similar results to the industry standard on only a $500 budget.